Okay. So, good evening again for the week 8 assignment, 8 section for Introduction to Semiconductor Fundamentals. And it's a course taught by Professor Naresh Imani from IIT Hyderabad. And I'm Shahzan Bhatt, currently a direct PhD student at IIT Bombay. So, uh, what we are going to do today is we are going to start from the portion we left at in the last session. That is I should say, the MOS capacitor characteristics. And we're going to advance into the something called as capacitance voltage characteristics of a MOS capacitor, which is extremely essential for the device characterization. I mean, I cannot emphasize more on this particular topic because it's of most importance in the industries currently. Whatever the industries are doing, they just need to take out the CV characteristic data of their devices. And that's what we are going to see what they do and how they particularly do it. So today, let's not start from the basic, from the scratch. That was actually kind of a ritual I used to start, but it used to take 30-40 minutes extra. So let's directly jump to the topic and a little bit revise briefly what we discussed in the previous session. So in the previous session, we talked about a MOS capacitor. A MOS capacitor. What is a MOS capacitor is something like if you have a metal and if you have oxide and a semiconductor, it may be a p-type or an n-type semiconductor. If you stack them like this, you get a structure which is called as metal oxide semiconductor. Okay, CAP stands for a capacitor. Now, there are some intriguing properties of this particular device, which I should say, which we studied. There are, let's say, there are certain regions which come because of application of the different biasing voltages. Let's say if you apply a particular voltage here, a particular voltage here, okay, then you get different regions, something called as accumulation. You get something called as depletion, and you get something called as inversion region. Okay, that you looked into the previous that you looked in the previous sessions. Briefly, we will discuss about it again. So let's for example, let me just add a page, few pages. Okay, so let's for example just briefly recap what we actually studied and where does these concepts come from. Let's say you have a MOS capacitor structure like this. It is this structure just rotated by a clockwise fashion by 90 degrees. Now you have a metal here, you have oxide here, this is oxide, this is metal, this is semiconductor. Let's take this as p-type semiconductor for the time being. Then what you do is that you connect it with the voltage source. Okay, let's connect it with the voltage source, a DC voltage source, not an AC voltage source currently. And what you can do is that you can understand the electrostatics of this particular device by using the band diagram. Okay, that you have earlier seen that how much important the band diagram is for understanding the carrier electrostatics or the carrier, I should say, the dynamics inside the particular semiconducting system. Now, let's start from the scratch. We first of all, let's say, are used to draw the band diagram, and let's draw it from the scratch. Let's say you have a oxide and you have a metal. Let's say this is a band diagram in equilibrium. In equilibrium, the Fermi level wants to be aligned. So this is the Fermi level of the metal. This is the let's say this is the Fermi level of the semiconductor. We are taking the p-type semiconductor for the time being. This is the Fermi level of the semiconductor. And the bands, let's say these bands are all flat at equilibrium. Okay, ideal condition. So this is not drawn to scale, just showing the signs. So what is going to happen is that this is the equilibrium band diagram of this particular MOS capacitor. When there is no application of any voltage, you just connected the whole thing in ideal scenario. This is ideal scenario. What does ideal scenario means? That there are no charges in oxide or whatsoever. Oxide is free of charges. Okay. So this is the assumption we are taking. That's why it's an ideal scenario. Now, just like the p-n junction, the Fermi level wants to be aligned, and you have a flat system, flat Fermi levels. Now, what is going to happen? What is going to happen is that now we are going to study this particular system under application of the bias, under application of bias. Now, what kind of bias? We are going to apply a bias like this. Now, I'll tell you the reason why we do it. This is a DC voltage, and this is a small AC voltage. It's called a small signal. Okay. So this basically small AC voltage rides over the DC. Let's say this is a DC level, DC G voltage, VG voltage. This is V versus time. Then the small signal rides over this particular voltage. Okay. It's very small as compared to that of this VG. So most of the carrier chains are basically brought about by this VG. And the small signal which is riding over it, it does not bring much change to the charges. We will see what it does. Okay. So we are superimposing some small AC signal to study about how the charges are responding at higher and lower frequencies. Okay. We are going to study that because at particular single DC level, we will not be able to know how the charges will respond. Okay, because in the end what we have to give to the device are some alternating fluctuating voltage levels, alternating voltages. That is what the device should be able to handle, and that's why we test the device for this particular small signal also along with the gate voltage, along with the VG voltage, which is the DC voltage. And let's assume that now, for example, if you have a p-type, you have a structure like this. You have a structure like p-type. That means it's an NMOS structure. It's an NMOS because this is particular is p-type, and this is an oxide. This is a metal. Now you draw. We start by drawing the band diagram of it. First, we apply the negative bias. Let's apply the negative bias. Negative in what sense? We apply the negative to this side and positive to this side, something like this. Okay, let's say this is V, this is the small signal AC voltage, and then this is the DC voltage, minus plus. This is VG. This is VS sine S sine of omega ST. Okay, small signal. Now, what happens because of it is that when you draw the band diagram, in the band diagram, you know that this is the oxide in between. Let's first show the oxide like this. Let's don't worry about the conduction bands, what happens to the conduction band of the oxide and valence band yet. What happens is because of this negative charge, the Fermi level on the metal side raises because negative increases the electrostatic potential energy of electrons. So Fermi level of metals goes up. This is the Fermi level of metal, EFM. It goes up as compared to that of this scenario. Okay, this raises because of negative voltage. Now, when the Fermi level of this metal goes up, on the other side, the semiconductor Fermi level goes down because you have applied positive voltage of it. So it reduces the electrostatic potential energy of electrons. Okay. Now, because this is a p-type semiconductor and you have applied a positive here, you have applied a negative here, you have applied a negative here. So it's as if the negative charges are kind of developing at the metal oxide interfaces. Okay, and because of that, you will see that there is a bending near the interface. In the bulk, the semiconductor remains as it was earlier, but near the interface, it starts to bend. It starts to bend like this. Now, why does it start to bend? Basically, this bending in the upward direction indicates that now, if an electron wants to, let's say, stay at this position, it has to spend more energy because there are negative charges here. And negative charges will repel the electrons on this side. So if an electron wants to stay here, it has to spend more energy, more potential energy to stay here. So that's what this band bending indicates. Okay. So now what happens because of this particular bending? The band bends in the upward direction because there are negative charges here. So the electrostatic potential energy at this particular position increases. So that's what the band bending shows. And now because of this bending, there are holes which get accumulated at this particular region. And remember, this is a p-type side, so here the holes are majority. Holes are the majority carriers. Okay, holes are the majority carriers, and you can find the N concentration as Ni squared divided by Na, because this particular side is doped with Na. All right. So these are the holes which get accumulated at this particular region. It's almost like a it's almost something like a two-dimensional hole gas. Don't worry about this term, but it's almost a huge concentration of holes get piled up at this particular place. Okay, now this is something called as accumulation. Accumulation is the accumulation of majority carriers at the oxide semiconductor interface. So this is the accumulated charge. This is the accumulated charge. In this case, it's a positive charge because of holes. Holes we consider as a positive charge. Okay. So on this side, these are negative charges. All right. This is scenario one. Now what we do, we had applied a negative bias here. Let's reduce the negative bias towards the positive end, and let's bring the bias from negative to positive. We have to go through the zero. That means let's apply a positive bias now. Earlier we applied a negative, we go through zero, and then we apply a positive bias. Let's apply a positive bias now. Now, what happens in this case? Let me take this. Let me duplicate this thing. Let me bring it here. All right. Oh God. Okay. So now what happens when we apply a positive bias? Let's remove this thing there. Let's remove this thing. For AC doesn't matter. I have to change the sign. Now let's apply the positive bias. This is the positive now. This is positive. This is negative. Let me draw a section here. Okay. So what happens because of positive bias now? Now it will reverse. It will change. The banding will change. How it's going to change? And yeah, remember in this case the oxide bending is in the same direction as that of the semiconductor bending here. Okay. Why? Because the electric field in this case will be in this direction, positive to negative. This is the electric field direction. This is the electric field direction in here. And you know that in the direction of electric field, potential decreases. Okay, so this particular bending of a conduction band or the valence band is actually electrostatic potential energy. So you know that electrostatic potential energy is minus q times electrostatic potential. Okay, and you know that electric field is equivalent to minus dV by dx, the gradient of the potential. From this you get V equals to minus E by Q. You substitute this here, you get minus of D minus E by Q dx. You get dE by dx 1 over Q. This is electric field. What does it indicate is that this negative sign here indicates that in the direction of the field, the potential reduces. Okay, because this particular thing is potential energy and not the potential. So that's why in the field direction it is increasing. It's opposite to that of the potential, because it's potential energy and there's a minus sign here. Okay, this is potential energy. This is potential energy. This is potential, and this is electric field, and and because of this, in the direction of the electrostatic potential, in the direction of the field, the potential decreases but the potential energy increases. That's what this particular sign, this particular bending is shown, because the field is in this direction, so the potential energy is increasing in this direction. In other words, the potential is reducing in that direction. So that's the scenario of the oxide bending. Now what happens for this particular case, when you have applied a positive bias. Okay, so what happens because of it is that you have again the oxide. Let's not draw the conduction band and valence band of oxide yet. We will see what will be the bending of semiconductor side. Then accordingly we will decide about the oxide bending. Because of the positive charge, you reduce the Fermi level you reduce the electrostatic potential energy of electrons on the metal side. Okay, this is now the electro Fermi level of the metal because you have applied positive charge. Okay, and on the semiconductor side, you have raised the Fermi level because you have applied the negative charge. And now, because you have now positive charges here at the metal oxide interface, and you have applied negative on the side, it's as if you are taking the electrons from here and dumping onto this side. So you're dumping the electrons now on this side. Okay. Now, what are those electrons going to do? You know, because this is p-type here, p-type means it has negative ions and holes, excess holes. So those electrons are going to fill those holes, and what will remain is only this negative charge, which is ionized, I should say, dopant, or I should say immobile charge. That is what happens in p-n junction also. And what are those immobile charges going to do? They are going to stay at this particular region and form a depletion region. Now that is what is going to happen. Inside the bulk, the band will remain same as it was earlier. There is no change in the bulk. The most of the change happen at the interface because of this particular charge at the interface. So it's like a capacitor action. Whatever is on the left hand side, the same wants to be on the right hand side to maintain the neutrality. Okay, if there is positive charge on this side, there has to be equal opposite charge on the other side of the oxide. Okay, so now the bending will take place. Now, how will the bending take place? This is the particular bending. Okay, now why does it bend downwards? Because you have positive charges here now. So electron will like to stay here. Or in other words, negative charges will like to stay here at this position, in particularly electrons, because at this position now the electrostatic potential energy has been reduced for the electrons because there is positive on the other side. So it likes to stay there. Okay, and this particular thing will bend like this. Okay, and the intrinsic level will be something like this. It's almost as if it is touching the Fermi level at this position. And you know this particular bending will be followed in the same direction as the direction of the bending will be same as that of the semiconductor. So this is the direction of the bending because right now here the electric field direction is in this direction because it's from the positive to the negative. Where is the negative? Negative charges are here because of the immobile charges depleted from the p-type side. Now this is the depletion charge, Q times Na. Okay, so these charges which get technically piled up there. This is called as depletion region. This is something called as depletion region. You have depleted the charges you have depleted the charges of mobile charges, and left is you are left with immobile charges only. Okay, which are these red charges, red shown in the red color. These are immobile charges, but these are necessary in order to uh, satisfy the condition on the right hand side, because there is positive charge on the left hand side. It should have some sort of negative charge on the other side of the oxide in order to satisfy the positive and negative charge neutrality. All right. So now what happens after it? Now we are yet to explain the what is the voltage range we are applying. We are just understanding the first of all the regions. Okay, now let's draw another thing, another regime. We have this MOS structure. We are now applying the same positive bias again, VG, but we are increasing VG now more. How much we are increasing, that is a separate question. We will discuss how much we have to increase. But we are increasing it beyond something called as threshold voltage. Threshold voltage. Now, what happens because of increasing the VG beyond this threshold voltage? That means these positive and negative, the voltage you are applying, you are increasing it so that it moves out of the depletion region now. Now it goes into another regime, and this regime is something called as inversion regime. Inversion regime or region. Now, what happens in inversion? Obviously, it should come after this particular region. Okay, it happens in a stepwise fashion. Now, what happens in inversion? You had this band diagram. Let me just take it here. Duplicate. Okay, it seems it's huge. Let's cut it. So you had this particular band diagram in the depletion. Okay, this was in depletion. This is the Fermi level, this is the this particular thing, and this is the intrinsic level just touching the Fermi level. And this is the Fermi level of the metal. This is the valence band of semiconductor, conduction band of semiconductor. This is exactly the depletion region band diagram. Okay, till now. Now, what happens in inversion is that you increase the voltage so much so that this bending increases now because you are not changing the polarity of voltage. The voltage is positive on the gate side, negative on the semiconductor side. But because of it, there is huge band bending now at this particular place. Huge bending. Why? Because you have increased the positive charges more here. And now because of it, you have already created a depletion charge, this particular charge in the depletion region. There are no more depletion charges which can be created. So what happens is that there is the electrons start to get generated. There is generation recombination mechanism now becoming dominant. Okay, they come from the bulk material itself. Okay, so now electrons start to get generated, and there are breaking of the bonds inside this particular semiconductor, and it generates those electrons. So it is as if that you had these ions stay there after the depletion, they stay there. So this is the depletion width, similar to that of p-n junction, made by these depletion charges. Now what happens? Electron and hole gets generated because you have increased the bias now beyond the threshold voltage. So an electron goes into this conduction band, leaves behind a hole in the valence band. This electron drifts down this potential and gets accumulated here. So these are so dense electrons now formed here. They come because of generation mechanisms, breaking of the bonds, and reconfiguration of the bonds now. Okay, they come from the bulk. And because there is this particular steep bending here, it indicates the gradient of the conduction band basically indicates the electric field, 1 over Q. And because of it, the drift current starts to flow. Okay, that means a drift. There is actually the drift of electrons from the bulk towards the interface, towards the bended region, because electron would like to go down the slope. Okay, there is the bend, and whatever electron gets generated here, it will like to go down the slope and get accumulated here. Because on the other end there are positive charges, it would like to stay there. So that is what happens in inversion. You have totally inverted the interface. It was p-type, but now the interface has been converted to almost an n-type region, which is also reflected in the Fermi level. The Fermi level is like this, but the intrinsic level goes down like this. So the Fermi level, this one, goes above the intrinsic level, and it almost touches the conduction band. That means in this region, at this region, the p-type gets converted to n-type. The p-type gets converted to n-type because now there are more electrons here. And this is what is called as inversion. This is what's called as inversion.
Excuse me, sir.
Okay, so
Hello, sir.
now there are electrons, there are depletion charges as well. So now we have to deal with it. Beyond that, this is it. We want the inversion to happen. Once the inversion happens, now we can play with these charges. That is what you will study in next lecture in something called as MOSFET. When you will go into the MOSFET, you will study about how you control these charges now, how you make it flow, how you turn it into ones and zeros, how you amplify the signal. But right now you are just studying MOS. Okay, you are studying MOS capacitors. And later on you will add something called a source and drain that will take these charges and the current will flow. Okay, right now here you are just inducing these charges. So this is what happens. These are the particular scenarios which are important for us. And whatever happens in the p-type, The same thing happens for the n-type, but the opposite, in the opposite direction. Let's say you had a this was p-type here, this was p-type here, this is also p-type. If you had, let's say, an n-type here, then you have to apply positive on the metal, negative on the semiconductor side to induce the accumulation. And in n-type, in if it was n-type in the accumulation regime, there would have been electrons instead of holes at this place, and the bending would be opposite. That's it. Other scenarios, you have to accordingly change the other scenarios. So for the n-type, it's inverse of the p-type. Whatever happens in the p-type. Okay, the opposite bending, the opposite charges get accumulated, the opposite charges get depleted, so on and so forth. Okay, so now what happens? Yet we did not talk about this particular small signal, small signal. We just varied this particular gate voltage, this one. Now we have to talk about small signal. In all these three scenarios, we didn't assume any small signal to be applied. We just considered that we are varying gate voltage. Remember that all this is controlled, the transition from accumulation to depletion to inversion. It's controlled by the gate voltage, this one, not the small signal. Small signal is just very small to perturb it, to kind of disturb the little bit of charges. It does not create the inversion regime or the accumulation regime. Okay, that's what we are going to see now. So what happens because of small signal analysis? Now you have all three regimes again, but let's talk about here now. Let's talk here only. Let's talk here. Let's say if you add a small signal over the, let's say you had negative here, you had positive, applied positive here, and now over the DC voltage of VG, you have a small signal oscillating. Because of it, in accumulation, there is going to be, I should say, rather no significant change. Okay, because it's very small. Let's say if we draw the charge profiles of these, let me draw the charge profile of this particular figure, because that will clear the I should say the significance of the small signal. Duplicate. Let me bring it here. Let me remove this thing, this thing, this thing. This thing goes. What happens when you apply a small signal? Can't we have inversion of the interface by applying a stronger? Yes. Can't we have inversion of the interface by applying a stronger negative for a MOS with p-type bulk? What are you saying? Can't we have inversion of interface
Hello, sir. Am I audible?
by applying stronger negative voltage? Okay, if we apply stronger negative voltage with p-type bulk. Okay, I got your question. You're saying in this scenario, if we go on increasing the negative voltage, what is going to happen? That is a very good question. Wouldn't the band bend other ways? Other way it cannot bend. No. Your first question, you had thought it clearly, but the other way it cannot bend. What will happen? I'll tell you. If you go on increasing the negative voltage in the accumulation range, okay, these bands will bend further. ऐसे होगा ऑक्साइड का बैंड, ऐसे होगा ऑक्साइड का बैंड. This will bend like this. This will bend like this. Concentration of holes will predominantly increase at this particular position. Fermi level will be almost like, not like this. Fermi level will be almost like here. This is the Fermi level. This is the conduction band. This is the valence band. The metal Fermi level will be here. This is what will happen. And what is going to happen beyond that? Beyond certain point, definitely there is a limit. You cannot go on increasing the negative voltage. But this band will not bend in opposite direction because you are not changing the polarity. It is still negative here, positive here. Negative here means there will be negative charges here. Okay. And positive means there will be the holes accumulated at this particular position, which are the majority on this side, majority carriers. Majority carriers. Okay, now this is so dense hole concentration now here that definitely there is a certain limit of voltage you will apply to the device. Okay, first thing. Second thing is if you go beyond that particular voltage, this particular oxide can break down and the device is damaged. What is breakdown? There is a particular threshold of electric field that an oxide can sustain. If the electric field value surpasses the breakdown field, the oxide breaks down and you get a flow of charge in this direction. And the device is of no use because then you don't have any oxide in between. Okay, there is no field effect now because electrons will directly move. It is as if the oxide will become conducting now beyond certain negative voltage. That negative voltage is huge. That's why we don't go beyond a very some let's say some huge negative values. Okay, we rather don't even go to the huge positive values as well. That is, there is a limit how much positive voltage you can apply to a particular structure. Otherwise, this particular case of dielectric breakdown can even happen in case of positive applied voltage. Okay, so this particular bending is so huge that there are n number of, I should say, many processes that can happen. This is one process, the breakdown of the dielectric. Another process, there is an electron here. Let me let me zoom this one here. The bending will be so huge in the oxide, yeah, oxide. The bending, this bending, it will be so huge that जो यहाँ पे इलेक्ट्रॉन है फर्मी लेवल मेटल की क्योंकि बिकॉज यहाँ पे बहुत सारे इलेक्ट्रॉन्स है देयर आर सो मेनी इलेक्ट्रॉन्स डेंस इलेक्ट्रॉन्स नाउ बिकॉज यू हैव अप्लाइड हायर नेगेटिव वोल्टेज as per your question. These electrons, for these electrons, this particular barrier, it is like a triangular barrier, and they will tunnel through, and they will appear on this particular side in the semiconductor side. यहाँ पे. This is something called as tunnel breakdown. Tunnel means ये अगर ऐसे barrier है triangular, electron wave function leaks appears on the other side, and it gives rise to the current, gate current in this direction, which is not desirable in your logic gates or logic circuits which control your ones and zeros. You don't want the current to flow in the toward from the gate towards the semiconductor side. That's why there is this particular oxide. You just want the charges to get induced. You just want these charges these charges to get induced. You don't want the charges to flow. Otherwise, all of the field effect action is lost. Okay, hope that answers your question. But it was a good thought. So let me remove this. Okay, so why can't we have accumulation, depletion, and inversion modes for metal semiconductor junctions? Because there the charge is actually flowing. There is no oxide there. Okay, metal semiconductor junctions, there is no oxide in between. Oxide prevents the flow of charge. That's why there are only two regions. Either it bands up, it bands down, either it's rectifying, either it's Schottky or ohmic. Got it? Metal semiconductor. If it bends like this, there is real flow of charge from this region to this region and this region to this region in metal semiconductor junction. But here, there is no flow of charge from metal to semiconductor. That is the basic difference. Because in metal semiconductor junction, there is no insulator here. It's an interface directly connecting two conducting systems, metal and a semiconductor. Hope that answers your question. Okay, let's move forward. Let's draw the charges for the small signal case. When we draw the charges, let's say we have this particular system. This is the we want to draw the charges in the system. Let's say we have just applied the VG right here, negative VG. Then there will be some, I should say, negative charges here, negative charges on the gate side, minus Q, and there will be positive charges on this side, plus Q, which are the holes. So these are the holes basically. These are negative electrons. Okay, so this is when you apply VG equals to negative, only VG equals to negative. So just follow the color coding because I'm going to use the same color in drawing the charges and showing it. Now, when you apply small signal, it's very small. It's going to slightly increase the positive holes on the P side. That means this is going to increase like this. This is plus delta Q charge. Let's say dq charge, and the same is going to appear here minus dq charge. On the metal, there are so many electron reservoirs present that it doesn't matter to it. Well, I mean, there is slightly increase in the negative charges because already there were so many negative charges. So it slightly increases these charges. That is when Vg is negative. Now, what happens when you have the you invert it? Let's say when Vg is equivalent to positive now. Okay, you go into this was accumulation region. Now you have the depletion region. We're talking about the depletion region. Now in the depletion, you have positive charges here. You have the positive charges here. That means positive charges on the metal side. These are positive charges plus Q. And you have the depletion charges here, which takes up some uniform distribution, which takes up some space, which are spreaded. And this is called as W depletion width. So these are negative immobile ions, equal and opposite to that of what is on the metal. So these are Q times Na. Okay, now we apply the small signal superimposed over it. Okay, what happens because of it? Slight increase in these charges, again slight increase, because this is because of small signal. Let's say this is d, maybe dq charge. Okay, and the depletion width will increase by, let's say, dwd, small change in the depletion width, and the same positive charge will kind of appear on this side plus dq. This is because of small signal. Now that means this scenario indicates a small signal does not disturb the system to a significant extent. It does not change the region from depletion to inversion or inversion to depletion. Only gate voltage controls that. This VG. That's why this VG is important. The small signal is important for frequency analysis only. And when you operate the device, you're going to study it. That's what we are going to look into. Now, when you increase the VG, positive voltage increased. Okay, now you move into something called as inversion region. Inversion region. And in inversion region, what you have now, you have these positive charges now increased. Look at the amplitude of it. Sorry, you have this. Yeah, this was positive. You have this positive charge on the metal side. Okay, and you had this depletion charge already there. It stays there. These are immobile ions now. And you had already these small signal, a little bit of more charge because of the small signal. So this is now the overall depletion width. It does not go beyond that because you cannot have unlimited depletion charges in a system. Once it reaches the maximum depletion width at something called as threshold voltage, it does not go beyond that depletion width. This is the depletion maximum, W dip maximum. Okay, you cannot uncover more negative charges now. Whatever you wanted to uncover, you have uncovered those negative charges. Now you don't have any more negative charges in that particular system to uncover. So now, because this is a inversion regime, so there are electrons which get piled up here and near the surface. There are electrons which come up at this particular region. They want to stay at the surface because there is positive charge on this side. So that's why they want to stay at the surface. So this is negative minus Q, equal and opposite. Now what happens? You see that these are the scenarios, and just follow the color coding. You will understand everything. Now, now you have a scenario you have to jump into something called as capacitance because now you have some charges separated by certain dielectric. Now you have to deal with capacitance. And the small signal will come into picture. So small signal analysis will also be important for this capacitance analysis. Now, how and why these capacitances come into picture? Let's talk about this particular system. Let's talk about first this system in accumulation. Let me draw it like this. Okay, let's draw it in a better way. Now, first in accumulation, when you talk about capacitance, you have simply like a negative charge on this side, a positive charge on this side, and it's separated by a oxide here, which is a dielectric. So it's like a parallel plate capacitor, just like a parallel plate capacitor. Even if you apply small signal, there will be small change in the negative charge here, something like minus dq, and there will be small increase in the holes here, something like plus dq. So it's actually a dq by dv type capacitance. It's a varying capacitance, voltage varying capacitor. Okay. But overall, this capacitance is equivalent to Cox, which is equivalent to, the conventional formula, the capacitance per unit area. Remember that this is capacitance per unit area. Okay, so it will be equivalent to the permittivity of the oxide divided by thickness of the oxide, this particular thickness, just like a parallel plate capacitor. Now, transitioning into depletion region, what happens in the depletion region? You have the oxide capacitance, but you have the depletion capacitance here. That means there are two capacitors. First one is because you have the positive charge here, you have the negative ion charge here. Okay, you have the negative charge here. And other one is because there is also this particular depletion charge, reverse biased, just like the reverse biased PN junction, there will be a depletion capacitance. Okay, so now you have the oxide capacitance, Cox, and you have the depletion capacitance, Cdip. Okay, and now you combine them, you get two capacitors in series. And now you know the overall capacitance is 1 by C equals to 1 by Cox plus 1 by C depletion. This is the overall capacitance. Let me do this. And now you got something interesting here, which is 1 by C dip. And 1 by C dip, this particular C depletion, which is the depletion capacitance, it is equivalent to permittivity of the silicon divided by the depletion width. Okay, and this depletion width is equivalent to under root 2 epsilon by q 1 by Na times the surface potential. And this surface potential, it's similar to that of p-n junction. 2 epsilon by q 1 by Na. There we had 1 by Na plus 1 by Nd, but you don't have any Nd here, so it's similar. This surface potential now can vary depending upon the bendings, and hence W depletion can vary. If this varies, C depletion varies. If C depletion varies, the overall capacitance varies. Now you have the changing capacitor here, which depends upon the depletion width, which depends upon the surface potential. Surface potential is this particular bending in this region, this particular bending. It represents the potential near the surface. Okay, now moving on to the inversion region. In the inversion region now, you have the negative charges here, which are the electrons, because the surface has been inverted from p to n type. Now it's simple again. It depends upon now the I should say the frequency of the applied small signal comes into picture. Why does it come into picture? That is the important question. Let us say you have two scenarios. First is small signal, high frequency. Another is small signal, Low frequency. Low frequency. How much low and how much high? Let's say high is of the order of megahertz and low is of the order of few hertz. This is like this signal. This is like this signal. The small signal you have applied. Now the story actually, I should say the few interesting things start to happen. Now, what happens in case of a small signal when you have applied a high frequency at this case? And why don't we, what is the question? Why don't we consider another capacitor formed by the inversion charge semiconductor bulk, metal back contact of the bulk? Okay, good question. Why don't we consider another capacitor formed by the inversion charge semiconductor bulk and metal vacuum? But that's a good question. That's a good thought actually. I liked it. I liked the thought very much. But I'll tell you why. Because there is there are currents flowing in the bulk of the semi. There are electrons and other charges flowing in the bulk of the semiconductor. You cannot consider that as a static dielectric element in between. The thing is that where does these electron come from? They come from the generation recombination in the bulk of a semiconductor. You cannot consider that as a capacitor. You cannot consider that as a capacitor. You cannot have system like this. The only capaciting region is the only thing we consider a capacitor as is oxide capacitor and a depletion capacitor. This one. This is oxide capacitor, this is W depletion capacitor. That means we consider it like this. Now, what you are saying, I got your question. What you are saying that if there is negative charge here, there is negative here. How will a capacitor form? Okay, capacitor has to have equal and opposite charges on the other side. You cannot have a capacitor like negative on this plate and negative on this plate. It does not make any sense. Hope you got the answer of that question. Okay, so thanks for the for this query, and let me rub this particular thing. And if you can just write down your questions, then we can discuss it in detail at the end because it will break the session in between. Otherwise, I really like the question. So, what is going to happen? Let me remove this. Let me remove this. What happens at the high frequency and low frequency, and why we consider it only in inversion? We don't consider it only in inversion. We consider it throughout in the inversion as well as in the accumulation as well as in the depletion. You remember that I showed these regions in the accumulation also. They come because of small signal. And why don't we talk of high frequency and low frequency in accumulation and depletion? That's what we are going to see. So let's talk about what happens in inversion when we talk of small signal first. Small signal, but with high frequency. Okay, a high frequency means that whatever the particular charges were inside this particular system. High frequency, first of all, if frequency is inversely proportional to time period of the particular signal. That means this particular signal will be so much fast oscillating that it won't give time for charges to respond. Now, which charges? That is the question. It is high, but with respect to what? It should be high with respect to something. Okay, now that's what we will be discussing. So let's consider this particular scenario. Let me show it here. Let me show first of all. mm, yes. Let me show it here. Let me take this particular thing. I'll take the band diagram from here. This and duplicate it. This is the concept where most of the people have confusion in. That why don't we consider it? So let me draw it here. So this is the accumulation region. Accumulation. Let me remove these colors. You know that in the this is the inversion region. This is the inversion region because you have electrons near this particular surface. So when you have inversion because of gate voltage, now you have small signal applied over that, and that small signal is high frequency. What happens is that you don't affect these electrons anymore. No effect on electrons. Why? Because you have to see where these electrons came from. They came because they came because of generation mechanism, generation plus recombination mechanism, particularly generation. From what? From bulk. I showed you in the previous picture that from the bulk, electron gets here, leaves a hole, electron gets here, generated, and then it drifts down and comes to that particular region, well, comes to that potential where it inverts the surface. And for this particular generation to happen, you have studied in previous lectures, this is the generation mechanism. For this generation to happen, the generation is change in electron concentration divided by some time constant. There has to be some time associated with it. It takes some time for the electron generation to take place. It does not happen instantly. And that is governed by this particular time constant, the generation time. And this generation time is of the order of microseconds. That means it takes few microseconds for that particular generation to take place. Okay, now why that is the reason under high frequency of the order of megahertz, there is no effect on electron concentration. Why? Because the high frequency, or I should say the high frequency which is in megahertz, the time period of it is approximately microseconds. That is equivalent to the generation time. Okay, or rather, that is much greater than the generation time. So electrons are not able to respond or get generated because of that small signal. Okay, so that is the reason that under high frequency these electrons don't get affected. Now, why? What happens at low frequency? Low frequency means the let's say this was the high frequency signal. Let's say this is the low frequency signal. This particular thing was in, let's say, 1 microsecond. But if your tau generation was, let's say, 5 microseconds, that means you are just giving the signal for 1 microsecond, but your generation time is 5 microseconds. It at least needs 5 microseconds to get generated, but you are removing the signal before that, small signal. So the electron won't get generated. Done. You don't get any electron generation. You don't have any effect of the high frequency. But for this case, let's say this was the time period. Let's say this is of the order of this is low frequency signal. That means this is huge time period. This time period is huge, and it will give enough time for the generation to happen. Okay, let's say this is milliseconds, so this is much greater than 5 microseconds. That means you have given enough time for the generation to occur. So that's why under high frequency and low frequency, these two particular scenarios happen. And that is why under accumulation and depletion, this does not happen. Why? You see that in the accumulation and depletion, it does not affect because in the accumulation, the holes get accumulated. Here, this. And these are the majority carriers. These are the majority carriers in p-type. They don't have to come because of generation or recombination mechanism. Okay, they don't have to come because of that because they are majority carriers in that. So they can just, I should say, quickly respond to the applied high frequency signal. And why do they quickly respond? Because there are majority holes present in that system. They are not created by the generation mechanism, just like the electrons created. And there is a time associated with it, something called as dielectric Maxwell relaxation time. It is approximately equivalent to the epsilon, the permittivity of the medium divided by conductivity. And you know, like from the Drude model, the electrostatics from the Drude model, the conductivity is, because these are holes, it's P times the charge of holes times the mobility. This is the concentration, this is the charge, this is the mobility. And if you have free holes in the system because it's a P type, then this P increases. P is more. It means sigma is more. That means the conductivity is more. This is more. The dielectric relaxation time is less. This relaxation time is less means they will respond fast. This is less means tau is of the order of 10 to the power minus 12 to 10 to the power minus 13 seconds for the majority carriers. Okay, so they will abruptly, I should say, respond to the high frequency signal. Even if the signal is this high frequency, obviously it should not be the high frequency of the order beyond terahertz. Then other scenarios will come into picture. But the time period of this signal should be of the order of or less than 10 to the power minus 12 seconds, or I should say the greater than 10 to the power minus 12 seconds. It's 10 to the power 12. So that is why the majority carriers are going to respond to the high frequency signal, but the minority carriers, they don't respond because they are created by generation mechanisms and there is a generation time constant associated with it. So in accumulation as well as in depletion, it happens because of majority carriers and there is a relaxation time associated with majority carriers. So that relaxation time or the Maxwell time is very small. It is of the order of, if you convert this into frequency, it is of the order of, it's of the order of terahertz frequency. That particular relaxation for the majority carriers. That means unless and until your small signal is not of the order of terahertz, it's not going to, I should say, it's not going to create any such non-ideal effects. It's going to create the holes, and these majority charges are going to respond abruptly. And that's what happens in metals also. Even if you give a metal a very high frequency signal, electrons are going to respond quickly to that particular signal because there are free electrons present in that system. Similarly, if they are whatever the free carriers are present in the system, whether they are electrons in N type, holes in P type, they are the majority carriers. The majority carriers respond with this time called as dielectric relaxation time, and they respond quickly to the high frequency signal, and that's why there is no significant effect, I should say, seen in the small signal and small signal high frequency and small signal low frequency analysis of the capacitances in the I should say MOS capacitor analysis. But right now we have just talked about the charges. What happens when we draw this capacitance versus voltage? Now you have everything. You have the oxide capacitance, you have this particular overall capacitance in the depletion region, and then you have the inversion capacitance now depends upon two modes, whether the small signal applied is high frequency or whether it's low frequency. And that's going to reflect in capacitance versus voltage curve. Now, if you draw the capacitance versus voltage curve, let's say this is capacitance here, this is voltage, but gate voltage. Note this voltage. This is a gate voltage. Okay. Now, in accumulation, you know that overall capacitance is oxide capacitance, which is epsilon ox divided by thickness of the oxide. And this is overall constant. If the oxide thickness is constant, epsilon oxide is constant. So this is going to remain constant up to certain value. So this is C accumulation, which is C oxide. Now, what happens? You have up to this particular value. This is V gate 0. In this region, V gate was negative. In this, V gate is positive. But once you go from negative to towards the 0 towards the positive side, you change the capacitance. Now you have the depletion capacitance. And you know that overall 1 by C is 1 by C aux plus 1 by C depletion. Okay, so you get a curve something like this up to this particular point, up to this particular point, something called as V threshold. At this particular point, now you have to increase the VG more. Okay, this particular region is depletion region, capacitance, up to the threshold voltage. What happens at threshold voltage? You increase the gate voltage more. But now it depends whether you increase along with the high frequency small signal or a low frequency small signal. If you have high frequency small signal, electrons are not further going to respond. It will stay like this at something called as C minimum capacitance. And if you have low frequency, it will go back to the original, this particular line. Okay, so that will be again reach to the original capacitance value. And this is beyond threshold voltage. Now you have this particular region as inversion. You have this particular region as inversion. You have this particular region as inversion. And these two scenarios come because of the majority and minority charges responding differently to the high frequency, what I have previously discussed. Okay, in this particular region, you are dealing with majority charge carriers and they respond fastly to the changing high frequency. So that's why there is no change with high and low frequency in accumulation as well as in depletion. But once you go in inversion, you are dealing with the minority charges at the interface and they come because of generation mechanisms, and that is a slow process. And if your high frequency is much faster, you cannot generate electrons, you cannot change the charges, you cannot change the, I should say, the capacitance anymore. So that's why this particular stays constant. This is for high frequency, this is for low frequency, and this something called as CV characteristics of a MOSFET. And this is for NMOS. NMOS means it's a p-type substrate where the channel after the inversion is having electrons. Okay, now this is the overall scenario of a capacitance versus voltage relationship. Now you see that if you go on, let's say, increasing the temperature, more and more electrons will get generated. And you see this particular curve shifting like this, like this, like this, like this. This is with the increasing temperature. And finally, it can combine with the low frequency curve. Even if you have applied the high frequency, still this will increase in the upward direction if you increase the temperature, because more electrons will get generated. That is as simple as that. More electrons will get generated in the inversion region. This is inversion region. Here, you get more electrons generated. They will again drift down. They will increase the charge concentration. Okay, so that is the overall effect. Now, what is going to happen? Let me just see what have we covered. Okay, whether is there any question? No. Just give me a few seconds. If you have any question, you can just ask. When the inversion charge is formed, does electron generation also take place in the already formed depletion region too? Hmm. What do you mean by when the inversion charge is formed? Inversion charge is itself, they are the electrons. Does the electron generation also take place in already formed depletion? Yes, correct. It can take place. It takes place. It takes place throughout. Whatever, but wherever it will get generated, mostly near the banded region, they will drift down. towards that interfacial region. This one. Whatever gets whatever gets generated, wherever it gets if it gets generated here, electrons, because there is a bending on the other side, on the left hand side of electron, they will get drifted down here. They will get accumulated here. And it gets generated throughout. Yes. No, 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 it gets throughout. You're right. Okay. But if it gets if it gets generated just near this banded region, oops, just near this banded region, it is, I mean, those electrons are going to drift down very fastly and go into this well. It's like a well for electrons. This is like a well for electrons. Okay. The numericals mention that MOSCAP gate is formed using N plus polysilicon. Why not use a metal instead? N plus polysilicon has a behavior similar to that of metal. N plus means very highly doped polysilicon is something a different term. Let's not go into jargon. But N plus means it's so high doped it almost behaves like a metal. Okay, and there are many reasons. There is a, I should say, fabrication point of view. There is one reason. Physics point of view, there is other reason. But mostly, you are studying here metal oxide semiconductor right now, and you will see in the upcoming videos why polysilicon is necessary for instead of a, because silicon dioxide forms a good bonding when you do the fabrication. They form the good interfaces. Okay, and N plus is almost like a metal. It's as if there is Fermi level gets into the conduction band of the silicon. That is what N plus means. And that behaves almost like a metal. And you get a good fabrication, I should say the interface. And there are several reasons also, but let's not go into the more deeper reasons. So you got it. Okay. One more, just last one interesting thing, then we will directly jump into the numericals because numericals are just the, I mean, they come from these concepts, whatever I discussed. If you understood these concepts, you can just, the numericals are just a cakewalk for you. Just one thing I want to mention here, it just came into my mind that if you had a, you know, where these basically these important or interesting phenomena are used. Definitely, these are used currently in your processors. This is what is happening in your processor right now. You are changing from accumulation to depletion to inversion region inside your MOSFETs. That is basically turning your MOSFET on and off. And how that is done, you will look in the upcoming courses in this particular course. Just give me a second. So, but one important thing it just came to my mind because of this polysilicon. You know about semiconductor memory. That is also based on this particular concept. Semiconductor means you might have heard about SSDs or NAND memory or flash memory, all based on semiconductors. They also have a similar system. There you have a oxide, semiconductor, oxide, semiconductor, semiconductor. Or let's say this is polysilicon. This came to my mind because of this polysilicon. Let's say this is polysilicon, this is polysilicon, this is semiconductor. All this is semiconductor in the end, and this is oxide. This is the structure of a simple memory block. How you create a memory of a let's say inside a SSD or a NAND or a flash. What you do there, you apply certain voltage so that this particular region goes up, this goes down, this also goes down. Let's say you apply negative and positive here. You have a band bending like this, let's say like this, like this. Let's say this goes like this. I'm showing it as roughly. You won't be able to understand the deeper electrostatic of it because these are two coupled MOS capacitors right now. But I just want you to think of this concept. You know what happens? Because there are electrons on this side, when you increase the negative value beyond certain threshold, the question you asked me that why don't what happens when you go on increasing the negative voltage beyond certain range? If you increase the negative voltage in this particular system, in this system where you have this particular semiconductor, these electrons can tunnel through this and they get accumulated here, and then they are trapped here. They cannot move. They are mobile electrons, but now they cannot go to this side or this side because there is oxide. And then you remove this particular bias, and it changes back to this particular system. Let's say because there are now electrons here, so little bit of, I should say, bending stays in the opposite direction. Let's say this particular is negative to positive. There will be, let's say, positive charges here, positive charges on the, let's say, on the other side, and let's say this is like this. There is negative, there is this, these are the electrons now. I just want to give you the flavor of it, application point of view. Don't think of the electrostatics right here. So the electrons you tunnel through the oxide, this they stay here in this semiconductor, यहाँ पे pile up, and this is actually the memory. You have created a memory, you have stored electrons. Now you store these electrons, you you have created, I should say, a region with capability to, I should say, extract and store the electrons on demand. And you can store these electrons for 10 years. That's what you do in your flash memory. Now, what happens when you have to read it? You have to apply again some current to extract these electrons, or you have to apply some voltage again to extract these electrons. These electrons come back, then you can read that current as a current values that gets converted into the whatever information you have stored. But that's a very complicated concept. But what happens, because you have stored these electrons here, with time, some of these electrons leak. Some of these electrons, let's say you have stored 100 electrons here, 5 electrons leak out. Your memory is still fine. You don't get corrupt memory or SD cards or memory cards or flash. Your memory will be fine. There is a certain threshold value up to which if the electron leaks, your memory will be fine. But if, let's say, 60 electrons leaked out with time, let's say in 2 years, 60 electrons leaked out. Now you have only 40 electrons remaining. Now, when you go on reading these electrons, you won't be able to retrieve your stored data after 2 years. That's why you should never leave your semiconductor memory unused. You have to use it with time again and again so that these number of electrons stays the same every time you use. Whenever you use a semiconductor memory, these electrons get refreshed. If there were 100 electrons initially, if let's say in 2 years 20 electrons leaked, 80 electrons are left, you are still able to see your data. But let's say if 40 electrons leaked, your data will be corrupt. You won't be able to see what was the data. That's why if you use it after 1 or 2 days, you refresh these electrons. You fill the 100 electrons back. Let's say then after 2 days, maybe 2 electrons leaked out. You have 98 electrons. You connected the USB to your computer again. You refresh these number of electrons. 100 electrons are coming back. Then it leaks again. Then it refreshes again. That's why this semiconductor memory cycle goes on. And that's why you have to use your semiconductor memory in order to keep these electrons refreshing. If you don't use it for a long time, these electrons leak out and your memory is gone. That's what happens in semiconductor memory cards, or mostly the flash memories and other things. But this is a very complicated concept from electrostatic point of view, but I just wanted to give you a flavor. It just came into my mind from this polysilicon concept. But this is how a memory works. All of these things you are learning, these are just the, I should say, the industry standard things or whatever is used in the chips and the memories. So let's move on to this region. We discussed about the polysilicon. We discussed about the polysilicon, or not the polysilicon. We discussed about this is the p-type semiconductor. That means we are talking about the NMOS currently here. This is the overall CV characteristics of this particular device. Okay, so now you have something called a strong accumulation. You have something called a strong inversion. This is something called a weak inversion. Let's not deal about the weak inversion and weak accumulation. These are just the names given to it. And you notice that this particular is the minimum capacitance, which is equivalent to this particular value. So you have C minimum at WD maximum. The capacitance will be minimum when the depletion width will be maximum because it is inversely proportional to the depletion width. Okay. And note that at this particular value, which is called as threshold voltage, threshold voltage, inversion starts to begin. So when V is greater or equal to V threshold, you have moved into the inversion region. Okay. And this V flat band is basically, it's something called as flat band voltage. Flat band voltage means it's the voltage you need to apply to make the bands flat. If there are certain, let's say, non-idealities inside the non-idealities, or if there is a metal semiconductor work function difference, this particular flat band voltage is actually equivalent to phi m minus phi s, and there is also fixed oxide charges divided by oxide capacitance. These are non-ideal effects. That means if you have the difference in work function, or if you have charges inside oxide, मतलब ये जो oxide है इसके अंदर charge अगर होगा, sometimes what happens when you fabricate, if you don't pay enough attention, you can diffuse the sodium ions here inside the oxide. These come from mostly from sweat. That's why in fabrication you have to wear those suits to keep everything clean. If you are sweating a lot and you are touching the chip, the sodium ions and the potassium ions from your sweat will get diffused into the oxide, and they will stay here. They will stay here, sodium ions. And these are immobile, these are very tricky to deal with. And because they will stay in the oxide, they will create additional bending inside the oxide. You know now there is a positive charge, so oxide में जो अंदर bending है वो ऐसे हो जाएगी because यहाँ पे positive charge है. ये अब oxide बनेगा. This is the oxide bending. Naturally, without applying any voltage, it messes up the system. It messes up with the charges inside, and it messes up with the threshold voltage also, because now there is inbuilt bending in the oxide. Now you have to deal with it first. Okay, so that's why flat band voltage considers all of these effects together, and it is the voltage you need to apply to make the bands flat, everything flat. When you have everything flat, then after you can move into the depletion and inversion region. Okay, so you have everything flat, then you can go into depletion region, and then you can go into inversion region. Okay, so that is the concept of flat band voltage. And now what happens is, this is the threshold voltage exactly. Threshold voltage is the minimum voltage you require to change from depletion to inversion region. Okay, and it depends upon, this particular thing is flat band voltage, both of these. That means if you want to go to the threshold voltage value, you first need to apply the voltage equal to flat band voltage. Then you go into the depletion regime. This is the depletion. These are the depletion charges, and this comes because of the inversion. Done. Threshold voltage. To reach the threshold voltage, you first have to make the bands flat. After making the bands flat, as you increase the gate voltage increased again, you go into depletion region. You increase the gate voltage further, you go into the inversion region. That is the overall picture of how you go from flat band to depletion to inversion region. Okay, so and the corresponding positive and negative have been shown for N channel and P channel. N channel means substrate is P type, that means NMOS. P channel means substrate is N type, that means PMOS. Channel means that electron inversion layer, that inversion layer contains which charges, that is denoted by, that's called as channel. This channel concept you will see more in MOSFET. Whatever the charges, inversion charges have, that is the charge of the channel. N channel means electrons are the inverted charges, electrons are in the inversion layer. P channel means holes are in the inversion layer. So this is the overall scenario. Let's jump into the questions now because we have less time remaining. So questions would be cakewalk now because these are the questions now which directly come from these concepts. Now you have a question first of all that a PG student has been given a MOS capacitor. He has to apply some small signal. Then he has to apply the gate voltage and the small signal. Small signal just to perturb it and to see the frequency response. This is versus the gate voltage CV. Now, based on the given data, we have to answer the following questions. First of all, the substrate doping and the type of MOS capacitor is. How are you going to see what is the substrate doping and what is the type of the MOS capacitor? That is the first question we have to answer. First of all, you see that this particular region is accumulation region, this particular region is depletion region, and this particular region is inversion region. And you see that why is this accumulation? Because capacitance is constant. Okay, and it's at the maximum value, this value, 120 picofarads. And this has been achieved by applying a negative gate voltage. This side is positive gate voltage, this is zero. Whenever you have the negative voltage and accumulation occurs, you know that it's a p-type. The scenario we showed earlier. You have the oxide, you have the negative voltage here, you have the holes accumulated at this region. So this is accumulation. Okay, so it's a p-type substrate and the type of MOSFET is NMOS. So it's a p-type substrate and the type of substrate and the type of MOS capacitor is NMOS. NMOS comes from the fact that in the inversion the channel will be N-type because if it is a p-type under inversion the channel will go to the N-type. As simple as that. Okay, so this particular region is inversion region because you have applying the gate voltage much greater than a value which is something called as this value, the threshold voltage. Okay, just give me a second. Okay, so this is the first question. Now the second question. And these particular things we have discussed, how you can vary the gate voltage. Basically, you can use something called as linearly varying gate voltage. What it means is that actually you do something like this. The slope of this is almost less than 0.1 volt per second. This is VG gate voltage versus time. You vary the gate voltage slowly in this fashion. Okay, then you measure the capacitance. You measure capacitance here C1, C2, C3, C4, and that those values you plot on this capacitance versus voltage curve. Capacitance versus VG. Okay, but you vary the gate voltage like this fashion, slowly, with this slope, 0.1 volt per second, voltage per second, less than 0.1 volt per second. So it's a slowly increased gate voltage. That's how you increase the gate voltage when you go from accumulation, to depletion to inversion. And after that, on this rides the small signal. That's what I showed. Small signal rides over it. This is the small signal sine omega t. That's what it is showing. Now the charge block diagram to point 2 in CV is given by what is point 2? This is point 2. Let me use the different color. This is point 2. You know the point 2 is almost this capacitance is minimum, C minimum capacitance. And at minimum capacitance you have maximum depletion width. Okay, this particular gate voltage here is threshold gate voltage, at least at that particular point. Right at that particular point, inversion has just started to happen. It has not happened. At threshold voltage, it just starts to happen. When the gate voltage crosses the threshold voltage, you have the inversion. Okay, so at point number 2, you still have the depletion region, but with maximum depletion width. Okay, so what happens is that in because earlier you noted that it's a p-type substrate. That means you have applied Vg greater than 0. That means positive Vg. But at this point, it is in this range. Vg is less than V threshold, greater than 0. This is the voltage range you are applying. And it is still in depletion. In depletion, you know there will be positive charges on the metal side. There will be negative immobile ions on the semiconductor oxide interface side near that banded region. Okay. And because of small signal is also applied, there will be slight more increased delta Q charges. Okay. So it is this scenario. Oh, sorry. Oh God. It is this particular scenario. Okay. So you have applied this particular thing is because of the gate voltage. Then this particular thing is because of small signal you applied. So this is the region in depletion. So this is the answer of this question. Why the other are not on answer of this question? Because this is not this even the scenario. Because you are applying positive, you are getting negative electrons. You cannot directly get negative electrons. You first will get depletion region. This is even not the case because you cannot get a depletion extra charge here. The extra charge has to be here, but at the end of the depletion region. That means it will increase the overall depletion width. This is the maximum WD maximum. At WD maximum, C will be capacitance will be minimum. That is what shows reflects in the graph. Okay, and this is not the scenario because this is inversion. This shows the inversion because these are the electrons just at the oxide semiconductor interface. So the correct answer has to be this. All right. So this is what he has also said that time constant of the order of 10 to the power minus 10 to 10 to the power minus 13 for the majority carriers at high frequency. This is what is called as the dielectric Maxwell relaxation time, which is epsilon divided by sigma. And for the majority carriers, it is of the order of 10 to the power minus 10 to 10 to the power minus 13 seconds. And even if you are giving it a high frequency signal, that they are going to respond anyway. Okay, if you are going to apply low frequency, they are going to respond because because the time period of it is still much lower than the time period it takes for the those majority carrier relaxations. Okay, but for the minority carrier, they come because of generation. Just remember this point forever. Okay, and now moving on to the other questions. Let's see what is the time here. Let's say we have the question number 3. If the area of the MOS capacitor is this particular thing, then the thickness of the oxide layer. We have to compute the thickness of the oxide layer. It can be simply computed because you are given the CV characteristics. You are given the CV characteristics like this. This is accumulation capacitance. Okay. So you have to compute the thickness. You can just use the accumulation capacitance value, which is epsilon oxide divided by thickness of the oxide. Epsilon oxide you have been given. Thickness of the oxide you need to compute. This has been given. This has been given as 120 picofarads. Use this value. You get epsilon ox divided by C accumulation. You're going to get the value of, I guess, 0.086. As simple as that. Just you have to do the calculation. There is no complicated concept here. But remember that you have to use the epsilon ox here, 3.9. Don't use the epsilon silicon in this. You can use it if you want to compute the oxide thickness by using depletion capacitance. In the depletion capacitance, 1 by C equals to 1 by C ox plus 1 by C depletion. In C depletion is equivalent to epsilon silicon divided by thickness divided by depletion width. Epsilon silicon is used here, not here. Okay, remember this point. Now we have the question 4. Question 4 means invoking the delta depletion approximation. The maximum depletion width in a MOS capacitor is this. This is the maximum depletion width occurs at inversion. I should say at the threshold voltage when the surface potential is 2 times the Fermi potential. The point 2 in the CV plot is what? Where is point 2? Where is point 2? This is point 2. Okay, let me draw it. So this is point 2. This is the minimum capacitance. This is the max capacitance, which is the accumulation capacitance. So this is threshold voltage. This is gate voltage. This is 0. So this is VG negative. This is VG positive. So what we have to find? We have to find the maximum depletion width. Again, you know that depletion width will be maximum when at WD maximum the capacitance will be minimum. That is this region. So you can directly use it. 1 over C minimum equals to 1 over C oxide plus 1 over C depletion. Everything has been given. Every single thing is given. C depletion is epsilon silicon over W depletion. W depletion is square root of 2 epsilon by Q 1 over Na surface potential. But surface they have said that maximum depletion width occurs at this surface potential, so you have to use this value, which is square root of 2 epsilon by Q 1 by Na 2 times the Fermi potential. Now the reason here is that we are not given the Fermi potential. This particular Fermi potential is basically the difference between the intrinsic level and the Fermi level in the bulk. That is the Fermi potential. So it has not been given. This is intrinsic level, and this was the Fermi level. This is the I should say the Fermi potential. But this particular potential is not given. So how are we going to compute it? We have to somehow compute it by using the C depletion value as whether it has been given or not. Let me just check. Uh, say the maximum depletion width occurs at this. Okay, and mm, are we given the particular? Is there some information missing? Let me just cross check it once. Maximum depletion width. Okay, where does this come from? Hmm. Okay. Yeah. Yeah. So what you have to do, because you cannot know the Fermi potential from this approach, what I just showed, this is the general approach, but from the figure, you are given this value, 40 picofarad. Directly use it here. You can directly use it, this particular value here. You can use C depletion is to be equivalent to epsilon silicon divided by W depletion. You can write it as, let's say, is this particular value given? Hmm, let me just recheck. Okay, I guess there is some issue. There is some information missing here. Hmm. So what you need to do, directly using this equation, you can write 1 by C min as the oxide capacitance, which is given in the figure. This value 120 picofarads. You can compute it as 120 picofarads plus C depletion. What is C depletion? I should say this is given. This is 40 picofarad plus 1 by C depletion. You find the 1 by C depletion, that will be 1 by 120 picofarads minus 1 by 40 picofarads. I missed this information. So you get C depletion from here. C depletion. You get the value of C depletion from here. I don't know what this value will be, but you can compute it easily. It'll be 120 into 40 divided by 120 plus 40, whatever this value comes. Once you get this value, you get the C depletion. You get the C depletion, you can compute C depletion is equivalent to epsilon silicon divided by W depletion. And you know, because you have computed it using the minimum capacitance value, so you know at minimum capacitance value, the depletion width will be maximum. So this is W depletion maximum. So you can compute W depletion maximum to be equivalent to epsilon silicon divided by C depletion. Done. You put the values, you're done. You have to put basically this value here. Epsilon silicon has been given. But don't mess up with epsilon silicon and epsilon oxide. Okay, that is it. That is the strategy for this particular problem. And you will definitely get the correct answer by this. You cannot use this particular approach because the Fermi potential is not given. If it would have been the case that you are given the band diagram, you are given the difference between the intrinsic and the Fermi levels, then you can easily compute it using this approach. But you are given the CV, so you can compute the maximum depletion width. Okay, moving on to the other question. The block diagram corresponding to point 3 and 4. Where is 3 and 4? Here is 3 and 4. 3, 4. Remember, this is inversion region. Okay, so this is interesting because you have, this is the low frequency region, this is the high frequency region. In this region, inversion charges don't respond because they are electrons, they are minority charges, they come because of generation, they are not going to respond at all. This region, low frequency, the capacitance value shifts back to the maximum capacitance because electrons are going to respond now in the inversion region. As simple as that. So now what you have to answer is the charge block diagram corresponding to this 3 and 4 are corresponding to 3 and 4. So what are the charge diagrams for 3 and 4? For 3, high frequency. Where is it? Where is it? First of all, they are both in inversion because gate voltage is greater than this value. This is threshold voltage. Gate voltage is greater than threshold. It indicates inversion. So that is why these electrons are shown in all of the figures. Not this one, but it's shown here. It's shown here. This comes, these electrons, these come because of gate voltage application. Now you have the high frequency and low frequency game turned on. Now because of low frequency, extra electrons will respond. So more electrons will, I should say, come up near the inversion region. But in the high frequency region, they are not going to respond. So for the high frequency 3, it should be D, and for the other case, it should be, I think the answer of this question should be yes. So the high frequency, it should be this particular scenario because under high frequency, no more electrons are responding. So whatever the electrons were, they were because of the gate voltage inverted. And under low frequency, this particular, you had the scenario which looks something like this. You have more response from the electrons now, and they get increased by small signal amount. This is because of small signal, low frequency. All right. Okay. Now moving on to question 6. The question is given that a student finds CVs. He gets two CVs when he does the measurement, and he finds these two CV shifted in y-axis and also in x-axis. This particular has one threshold voltage, this particular has second threshold voltage. So two different threshold voltages. And this has C minimum 2, this has C minimum 1, two different C minimum C minimums, minimum capacitances. So we have to find the which one is highly doped. Very interesting question again, but quite easy question. You know that this C minimum is related to 1 by C minimum is basically 1 by C ox plus 1 by C depletion. But at what depletion? C depletion is basically epsilon silicon divided by W depletion. But at minimum, W depletion is maximum. Okay, and W depletion, it depends upon the doping, 2 epsilon by Q, 1 by Na into surface potential. Now that means W depletion is inversely proportional to square root of doping. So if you increase this particular doping, you lower the depletion width. That means you lower the depletion width, you increase the depletion capacitance. You increase the depletion capacitance, you overall are going to reduce, or you're overall going to increase this particular, or I should say you can write this in a particularly in a good manner. You can write this C minimum is equivalent to C ox C depth divided by C ox plus C depth, or you can write it C, let's say, C ox divided by C depletion plus 1. This is C minimum. This way you can directly correlate the effects. Now if Na increases, W dip decreases. W dip decreases, C dip, what is going to happen to C dip? C dip increases. C dip increases, this overall ratio reduces. The denominator reduces, overall this is going to increase. You got the point. So you just have to keep in mind what happens to the W depletion, C depletion, and this thing. Because of reduction in the depletion width, the C depletion increased. Because of the denominator of this particular ratio decreased, this overall fraction is going to increase. And because of the denominator of this thing is going to increase, this overall will reduce. So that is overall going to reduce the C minimum. That means Na, I should say, if Na1 is greater than Na2, then WD1 is less than WD2. That means CD1 is greater than CD2. That means C min 1 is it ulta is greater than C min 2. That means C min 1 is greater than C min 2. This particular scenario, that means Na1 is greater than Na2. Is that the answer of this question? It should be. Yeah, that means Na1 is greater than Na2. This is the overall, I should say, the flow of this. One by one. Go from this to this, this to this, this to this, using this equation. Don't have to do any calculations. Okay, and threshold voltage also increased, but let's not evaluate it in terms of threshold voltage. Otherwise, you could have evaluated in terms of threshold voltage also, because the threshold voltage is phi ms minus the the interface charge divided by oxide capacitance plus the depletion charge divided by Cox. This can also be actually used to evaluate it. But let's not go into that method. But think about it. You can use this particular Q depletion here, and you can see what is the effect on the threshold voltage. You will see the increase in the threshold voltage for one and decrease in the other. But that will slightly complicated. But this is the exact, I should say, the analysis which can be done for this question. So let's move on to the question 7 quickly. The LFCV and HFCV curves are identical in accumulation and depletion. Correct. Is it correct? The LFCV and HFCV curves. You have the MOS. This is LFCV. This is HFCV. C versus VG. It is saying that LFCV and HFCV curves are of a MOS are identical in accumulation and depletion. Correct. In accumulation and depletion, there is no. Oh, let me just. Sorry for this disturbance. Okay, let the screen go. In accumulation and the depletion, there is no significant. There is no difference whether you apply the high frequency or low frequency. Why? Again, because of the majority carriers. Majority carriers respond with dielectric relaxation time, which is very small, and it doesn't matter if you apply high frequency or low frequency. They are going to respond very fast. So second one is accumulation and depletion are characterized by majority charges, which is much smaller than applied frequency. That is absolutely correct. So that means S1 is true, S2 is true, and S2 is the correct explanation of S1. That's what we had discussed in detail in the earlier part of this session. Okay, so now gate question, a gate problem, which is basically showing how to get the what we have to compute in this. A MOS capacitor is fabricated on p-type silicon. Metal work function has been given. That means if this is the vacuum level and this is the Fermi level of the metal, then this particular value has been given phi m, which is equivalent to 4.1 electron volt. The electron affinity of a silicon has been given. Electron affinity, if this is vacuum, you first always draw the band diagram of it. You will get everything clearly. If this is p-type silicon, this is conduction band, then this is the electron affinity of a silicon, which is 4.0 electron volt. This is the work function of a silicon. Okay, this is Fermi level of silicon. This is Fermi level of metal. EC minus EF, this particular value has been given 0.9 electron volt. And okay, if the measured flat band voltage is minus 1 volt, flat band voltage has been given as minus 1 volt. That means it's a non-ideal scenario. You have to apply the at least minus 1 volt first to make the bands flat, everything flat. After passing the minus 1 volt towards the zero, then you can go to the depletion, then go to inversion. Okay, basically this particular value we considered as zero, but we considered the flat band voltage earlier to be zero in all the cases. But if somehow you have the scenario like this, not like this, uh, let's say you have something like this, this particular value shifts to here, then this particular value is the flat band voltage and it can be negative. Okay, then you have to consider all of the cases again. You have to compute the things again. So it means that it will shift the threshold voltage also. Okay, threshold voltage will be shifted because remember in threshold voltage the contribution from phi ms minus in oxide charges minus oxide charges divided by Cox plus depletion charges divided by Cox plus twice the Fermi potential. This particular these two particular things come because of flat band voltage. This is basically the V flat band. Okay, the difference in the work function of metal and work function of semiconductor. And these are the interface charges, other non-ideal charges inside the metal, inside the oxide, sorry. So now what we have to do, we have to find the magnitude of fixed charges at oxide semiconductor interface. This is the concept about fixed charges at oxide semiconductor interface. So you have to find I should say the charge magnitude of the fixed charge at oxide semiconductor interface, oxide and semiconductor interface. Okay, so how we are going to approach this particular question? So what you do, initially you find the flat band voltage. You use this particular thing. Flat band voltage has been given. What you can compute from it is oxide charges. I showed you that flat band voltage is basically phi ms, which is the work function difference between metal and semiconductor, minus the oxide charge divided by oxide capacitance. And you can write these as phi m minus phi s minus oxide charge divided by oxide capacitance, V flat band. This every what is given, this is given, this is given, you will obtain this particular value. Okay, but you will obtain it in terms of what? In terms of Cox. When you do this computation, you get Qox by Cox is equivalent to VFB minus phi m minus phi s. Okay, everything is given. You can write it as minus 1 volt, or I should say the minus 0.8, and you get Qox by Cox to be approximately equivalent to 0.2. I think I messed up with the signs. Phi m minus pi s. Yeah, this will come out to be negative, and this will be 0.2. 0.2, yeah. So you will get Qox to be equivalent to 0.2 times Cox. Where you get the Cox? You can compute Cox as epsilon ox divided by thickness of the oxide. I think everything is given again. Is it given? Thickness of oxide is given. Epsilon oxide is given. Use this value. You can use 3.9. Basically, epsilon ox is epsilon naught epsilon divided by thickness of oxide. This is permittivity of the free space, which is 8.85 into 10 to the power minus 12 farad per meter into 3.9 divided by thickness of the oxide is how much? 0.1 micrometer, 0.1 into 10 to the power minus 6. You compute this value, you get the oxide value as approximately 3.5 into 10 to the power minus 8 farad per centimeter square. Take the note of units. Okay, this I took in meter, this is also in meter. But finally, you have to convert everything, whatever is given in the question. Most of the people mess with the units in the examination, and 99% of the students do it wrong because of just the units. Okay, they just mess with the units. You have to either take everything in centimeter or take everything in meter. Preferably, I will take everything in centimeter. Even take this as in centimeters if you want to do calculation, because most of the charges are given in per centimeter square or per centimeter cube in the gate examination and other entrance examinations. That will be beneficial. So you use Cox here, you get Qox. I think that's done. That will be the answer of this question, and you will finally get Qox to be approximately 6.9 nanocoulombs per centimeter square. And yeah, that's it. That's the answer of this question. Okay, what is this? Interface states subjected to high electric field for some time due to the breaking rearrangement of bonds. Okay. This raises reliability concern because threshold voltage and a transistor current would change with the usage and could potentially cause sensitive circuit failures. Yeah, this is the real problem. That is what I was talking about. If there are interfacial charges, apart from oxide charges, there are certain charges which remain at the interface of a metal and semiconductor. If there are certain charges here, there are certain charges here in the oxide. These all mess up with the, I should say, the threshold voltage. And if they mess up with the threshold voltage, they mess with the logic levels of ones and zeros in the system, because the threshold voltage is the voltage that actually you will study, that determines whether your MOSFET is in one state, on state, or off state. If it is greater than threshold voltage, it is in on state. If it is less than threshold voltage, it is in off state. And if you mess with the threshold voltage, you mess with the on and off states. You mess with the binary ones and zeros in the system. If you mess with the binary ones and zeros in the system, you cannot control the logic. You cannot control ones and zeros. You will get errors, and they fail the device, they fail the system itself. They cause the failure of the system. Okay, it's a very interesting fact, I should say. I mean, what I mean to say, all these charges which are present at the interface, because there is this is silicon dioxide silicon interface. So there are something called as dangling bonds here. Dangling bonds. These are unsatisfied bonds. All of the bonds, let's say this is silicon, this is silicon, this is silicon, this is the semiconductor side, P-type. So this is silicon. Maybe there is what is this boron. Then there is silicon. Then there is boron. Maybe then there is silicon. There is silicon, silicon, silicon. So, and here you have silicon dioxide, silicon combined with two oxides. Okay, silicon with two oxides, two oxides, and you have silicon here with two oxides. When the bond forms between these two particular silicons and silicon, or silicon and oxygen, all of these bonds are not satisfied. Or they don't, all of these bonds don't get combined. Okay, what it remains is some unsatisfied bonds, some bonds which do not find a other partner to make a bond. It leaves a so many number of bonds unsatisfied. So that forms something called as dangling bonds. And those unsatisfied bonds create states there, energy states. Now you have energy states here at the metal semiconductor interface. And you know, if you have energy states, electrons can stay there, holes can stay there, and it messes up with the system. So that's why the study of these particular interfaces is very essential for semiconductor physics, for all of the electronics industry. What happens at this particular interface, at this interface? This is this. If you can study it, this is still an open research problem of studying these interfaces. We can model it, but we cannot perfectly model it yet. So that's why it's an open research problem still. Uh, there are interesting facts which actually come at these particular interfaces. And similarly, these positive charges, which can be sodium contamination, potassium contamination ions, that can change the threshold voltage. Now, what these can do, because threshold voltage is phi ms minus q fixed charges inside the oxide plus q depletion divided by c ox, or c depletion, plus twice the Fermi potential. This is the threshold voltage. If anything among these changes, if the fixed charges inside these oxide and semiconductor interface change, threshold voltage is going to change. And if threshold voltage changes, it will change the scenario of how to interpret on and off state of a transistor. If let's say if let's say threshold voltage was 1 volt, that means you had to apply 1 volt to invert channel to turn on the transistor. But if let's say because of some fixed charges, threshold voltage went down to zero point 0.8 volt, now it will turn on before you giving the 1 volt. Okay, that is a danger. That is a dangerous scenario. It should not turn on by its own. If it will turn on by its own, it will cause power loss inside the device, because you don't want it turned on by its own, or turned on easily, or turned on automatically. So that's why a fixed threshold voltage is essential for a device. Okay. And just a brief fact that sometimes what also happens is that if in I mean, we are living in the universe which is full of radiations. Let's say we are living on Earth, and somehow deep in the universe, a star exploded. Let's say this was a star and it exploded, and it sent down gamma rays and other high energy particles towards the Earth. Some because our ozone layer can protect us from these particles, but somehow few particles go through and they hit us. Some few, very few. Some maybe some high energy particles. And on Earth, even in space, we have satellites. On Earth, we have mobile phones, other electronic gadgets. If those gamma rays, or not it's not as gamma rays, it's high energy particles. If they hit any of the mobile phone or laptop somebody using, and they hit this transistor in the electronic circuit, they can create electron hole pairs. This electron can go here, and it will change the threshold voltage, and a device may behave weirdly. Sometimes it also happens that whenever somewhere in the universe there's a star burst, people on Earth start to get some kind of, I should say, glitch in their devices, and most of the scientists believe it's because of it. It's a very deeper story. Let's not go into that depth, but let we can discuss it someday. So let's go to the question number 9. For a MOS capacitor, you have to find the depletion width variation for the varying gate voltage. All right. So you know that for the depletion region varies as a square root of the surface potential, and you can control the surface potential by the I should say gate voltage. If you have the square root variation with the gate voltage or the surface potential, that indicates something variation like this. Okay, so that is this particular thing is the answer of this question. It cannot be like this. It cannot be like this. It cannot have a it cannot have peak like this particular thing. It should be a smoothly varying function, a square root. Okay, and one more thing is that at the particular, let's say, when you go from flat band towards the gate voltage, you have the depletion. You go beyond the threshold voltage, you have the inversion. That means if gate voltage is less than threshold voltage, greater than flat band, this is the depletion region. If gate voltage is greater than threshold voltage, this is the inversion. Okay, this is the particular scenario. If gate voltage is less than flat band voltage, you are still in the accumulation mode. Okay, that's the overall scenario. Now, the final question is, this is the particular thing. It's and varies as a square root of surface potential. In MOS capacitor, capacitance at threshold voltage is due to at threshold voltage. That means this Vg. What is the capacitance due to? You know that this is C min. It is because of both the C ox plus 1 by C dep. So it's because of both oxide capacitance in series with the depletion capacitance. Okay, this thing. C ox, C dep. That's it. All right, so we exceeded our time today, and it was a good session. I enjoyed teaching it actually. And if you have any questions, you can just tell me, ask me. Otherwise, I'll just stop the session. Let me charge my pencil. I think okay, if you have any questions, can't we find W max once we find C depth since C min and C ox are known? Oh, I checked this your reply late. What you are saying? That was for question number 4. Yeah, I can read it. Let me just, can't we find W max once we find C depth? Yeah, that's what I think I did. Since even, that is correct. That's what actually I did later on. Thank you for this nice help. Okay, if you have any question, you can just ask me. Otherwise, we are done with this extreme electron device physics part, which is the favorite part I like to teach. It's very interesting. All right, this particular thing. If you have any question, you can stay. Otherwise, I'll stop the recording. Let me stop the recording.